Okay, thanks for coming. Okay, today we have the Robert H. Cuyler Endowed lecturer. Okay, and I'm gonna let Michael introduce Ken. It's Ken Belitz from USGS.
Welcome everybody, my name is Michael Young. I'm a senior scientist at the Bureau and I'm now your Associate Dean for Research. Now to introduce Ken, who we're really proud to have him here. He's the 2022 Birdsall Dryas Lecturer for GSA for this year. Ken is a supervisor research hydrologist with the USGS in Massachusetts. He received his BS in geology from Binghamton, what we used to call SUNY B back in the day, and a PhD in hydrogeology from Stanford. His dissertation was really looking at large basin scale hydrogeologic models, and his dissertation was on the Denver Basin. After completing his PhD, he joined USGS in California and basically focused on constructing the Western San Joaquin Valley groundwater flow model, which became the gold standard for the state and has been used ever since. And he took a 7-year sabbatical from federal service and taught at Dartmouth and Queens College in New York. And then following his sabbatical, he went back to USGS and in 1998 to lead the interdisciplinary team studying water quality of the Santa Ana River Basin as part of the USGS NAQUA program. Again, we're super proud, Ken, that you're here, and welcome to UT Austin.
Thank you so much for having me. It's really a thrill. UT Austin is one of the great centers for geoscience. It's really a pleasure for me to join you. The presentation today, the quality of groundwater used for public supply in the continental United States, is not the work of one person, but rather really a very, very large team effort. And there's a paper by the same title published in Environmental Science and Technology, and there's a dozen authors there, and each one of them really represents another team of people behind them. So I'll try to mention folks as I go, but it's a very large effort, and I'll try to share with you on some of what it takes to do that. I'll also note that Shirley Dryas is a graduate of UT Austin, as Jack reminded me, and she's also a great friend and a great colleague. My presentation will have 3 parts. I'll give you some background, the context for this work. I'll spend a fair amount of time on study design, and the study design is really important to establish the credibility of the work that we did to evaluate groundwater quality at both regional and national scales, and then I'll go into the groundwater quality assessment. I'll warn you, and you can raise your hand at any time, I can speak really fast, and so please feel free to slow me down. In the late 1980s, the chief hydrologist of the U.S. Geological Survey was testifying before Congress and was asked the question, what is the quality of the nation's water? And the chief hydrologist didn't really have an answer. Fortunately, the survey was not punished for that lack of a response, but rather was directed to answer it. And that really began the National Water Quality Assessment Program, or NAQUA. In turn, NAQUA took that mandate and asked 3 questions of itself. What is the quality of the nation's water? Is it getting better or worse? And what are the factors affecting water quality? Today, I'll focus primarily on that first question and a little bit on the third. I won't touch the second question. The NAQUA program was implemented in the surface water column, aquatic ecosystem health, and in the groundwater. The program organized itself into decadal cycles. Prior to the beginning of a cycle, about 2 years were spent planning 10 years of activity. I had the good fortune of joining the planning effort for the 3rd cycle, and one of the members of the planning team for the 3rd cycle had been in charge of public outreach and communication in the 2nd cycle. And I asked the question, what is the quality of the nation's groundwater? And the response was, it depends. Now that's a typical response of scientists that often leads to more funding. But I thought we really should be doing better than it depends. And today I hope that we have done better than it depends. The funding for the NAQUA program is still in place, but it was closed down in 2021. So it's no longer a centralized program, but there's still ongoing water quality work. In the 3rd cycle, we set out for ourselves that we would assess groundwater quality in 3 dimensions. In the first 2 decades, the Geological Survey's NAQUA program focused on two types of studies, land use studies and major aquifer studies. The land use studies were designed to address the question, how does human land use affect groundwater quality? And to answer that question, they focused on the shallowest groundwater, just below the depth of the water table. So those wells were typically drilled by the USGS, drilled to depths of 20 to 50 feet. There were several thousand wells drilled in that first cycle, but by the time the third cycle came around, the funding had stayed level, so we could only afford to resample about 1,400. In the first cycle of NAWQA, one of the primary organizational units was a study unit, and the study units were generally large watersheds or really important watersheds. And then the study units were asked, if there's an area within your watershed where domestic wells are an important source of water supply, go ahead and do a major aquifer study. So if you look at that map in the middle, you'll see there's a lot of clusters of points. They're broadly distributed across the country, but there's a lot of gaps between those clusters. These are domestic wells. In most of the United States, domestic wells are on the order of 50 to 150 feet deep, and we resampled about 1,200 of those wells in cycle 3. In the third cycle, we added a new component to really get at this third dimension, and that was to assess groundwater quality in the depth zone used for public supply. So we sampled public supply wells. Again, over most of the country, it's not exclusively true. Those wells are about 150 to 750 feet deep, and we sampled 1,500 wells. To give you some sense of the scope of this work, our field crews prep, they have a lot of bottles to get cleaned up, a lot of materials to prepare. They go out to the field, they collect samples, they're putting them into coolers, they ship them out to laboratories, they come back to the office, they clean up, fill out their paperwork. Those 1,500 wells represent about 5,000 person days. And our field crews typically put in a 10-hour day. So the work I'm presenting today is about 50,000 person hours, which is about 20 years of work. Not only could not I do all that work, I couldn't even supervise all of that work. So there's a lot of layers of folks really organized to do this type of work. So we're going to focus on these principal aquifer studies. We're not going to focus on the land use nor the major aquifer wells in this presentation. We're going to recapitulate the question that Congress put to the chief hydrologist, and we're going to ask the question, what is the quality of groundwater used as a source of public supply in the continental United States, or CONUS? That's a big question. It's really a little hard to tackle. So we're going to break it up into simpler questions. They're still big, but they can be answered. And today we're going to answer the first, second questions in detail, and I'll only touch on the third. Which constituents are most prevalent at elevated concentrations? How many people are potentially affected? What are the hydrogeologic and geochemical characteristics of the aquifers where elevated concentrations are observed? So 3 big questions. Those questions were addressed at the scale of principal aquifers. I'm going to ask you not to read those colors, just know enough that they're representing different lithologies of the aquifers. If I catch you reading, I'll talk really fast. Principal aquifers are laterally extensive aquifers that provide large volumes of potable water for human use. There are 67 principal aquifers in the continental United States. Well, we didn't focus on 67, we focused on 25. Those 25 principal aquifers account for 85% of the total pumping for public supply. I'm going to ask you not to read the colors. I'm going to ask you, though, to look at how those points are spread out. Those points are spread out across each of those principal aquifers. And again, I'll return to this several times in the presentation, so you don't have to kind of get into the details quite yet. So we've got 25 principal aquifers that we're going to focus our evaluation on. That's the background. We're talking about the National Water Quality Assessment Program. It runs in decadal cycles. We're going to focus on one component of groundwater in the third cycle, which is principal aquifers. What makes our study possible is the use of equal area grids, and that we sample for a large number of constituents, and we compare those concentrations that we sample to health-based benchmarks. So let's start with equal area grids. This is what an equal area grid looks like for the Floridan aquifer system. And you'll see those gold shapes are broadly distributed across that Floridan aquifer. And you'll notice they're not equant, they're not equal in shape to each other. However, every one of those polygons, as we'll call it, has exactly the same area as any other. So those are equal area grid cells. Then what we're going to do is go to every grid cell. obtain as much information as we can on all of the public supply wells in that grid cell. We're going to randomly sample one. Unfortunately, people have called this random sampling, but it's not random sampling. It's stratified. It's stratified on equal areas. If this was random sampling, the wells would be clustered in those places that are the most public supply wells. So we're broadly distributing our public supply wells across the full extent of a principal aquifer. Now we're going to walk you through a set of cartoons to kind of help develop some intuition. Imagine you have a 10 by 10 grid, and in 9 of those cells, it's filled with blue balls. So imagine taking this room, divided up into 10 rows, 10 columns. There are bins. And every bin, just fill it with white balls in 91 and fill it with blue balls in the corner. Put a canvas over the whole thing, punch a hole, pull out a ball. So we're going to obtain one sample from each one of those 100 cells. And in this cartoon, we will obtain exactly 9 dark samples in our sampling. There's no choice. We can infer from our sample that the underlying proportion is 0.09. In fact, you can't miss in this cartoon. So we can infer that it's 9% dark blue balls. Let's take that set of 9 cells. Let's call it a target. Let's move the target to the middle. Let's move the target across the top. Let's just distribute that target throughout that area. Let's obtain 1 sample per cell. We will again obtain exactly 9 blue samples. We can infer that the underlying proportion is 0.09. If we would like to infer that underlying proportion, how much of the domain is blue balls, it doesn't matter where they're located, and it doesn't matter how they're distributed. Let's take that 3 by 3 and let's expand it to a 6 by 6. And we're going to expand it such that each one of those light blue cells is 25% dark blue and 75% white balls. So you can imagine it as a 1 by 4 or 4 out of 16. When we sample one of those light blue cells, there's a 1 in 4 chance it will be dark blue, or a 4 in 16, which is also 1 out of 4. So now we're going to, once again, obtain 100 samples. So imagine we've got 100 bins, but there's 6 bins by 6 bins, so there's 36 bins. And when you look at each of those bins, perhaps it's divided into 4. You can't see it, so you will either get a blue ball or a white ball. In any one of those light blue, there's a 1 in 4 chance of a blue ball, a 3 in 4 chance of a white ball. But when we sample those white cells, we will get exactly 64 white samples. There's no choice, there's only white balls. The remaining 36 cells will most likely produce 9 dark blue balls. But we could get 8, we could get 10. The chances of getting no blue balls is not that high. The chance of getting 36 blue balls is even lower. Well, let's take that 6 by 6 area, again recalling that it's 25% dark blue, move it to the center, move it across the top, simply distribute it. Once again, in each one of those images, we will get exactly 64 white samples. The remaining 36 cells will most likely provide 9 darker blue. So again, it doesn't matter the location nor the distribution of those light blue cells. Well, finally, hopefully that shows up. The color match is not that great. The grid there, imagine it's all light blue. So now the target is present in every one of those cells. So every one of those cells is 0.09. So imagine it's a 3 by 3. So we have this room that was 100 cells. Each one of these cells is now 3 by 3. And in that 3 by 3, one of them is dark blue, and the rest are white. Now we're going to once again sample. Now, when we sample each one of those really light blue cells, and here it's really light, there's a 1 in 9 chance in any one of those bins to get a dark blue, and an 8 in 9 chance of getting a white. The most likely outcome is still 9, because it's 9%. However, the chances of it being 8 or the chances of being 10 are nearly as great as 9. The chances of 7 and 11 are a little bit less because we are starting to deviate from the underlying proportion. The uncertainty has now increased, right? It was perfectly structured, no uncertainty, you can't miss. When it's perfectly dispersed, that's our maximum level of uncertainty. So again, with equal area sampling, we divide our principal aquifer into cells of equal area. We obtain 1 sample per well, 1 well per cell. The most likely estimate of the aquifer scale proportion that we don't know is the observed detection frequency. The estimate does not depend on location, shape, nor distribution of high values. This next line is completely obvious and also really subtle. Proportion is scale invariant. Now, in every other state of the union, I say, we're going to sample New Jersey, we're going to sample Texas. But instead, I'll say we're going to sample New Jersey, and we're going to sample California. And we would like to evaluate the groundwater quality of those two states, and we're going to use proportion as our metric. What proportion of the groundwater has elevated concentrations? If we would like to have an answer of equal certainty for New Jersey and for California, we need the same number of wells. It doesn't depend on how big it is. That can be really upsetting. And it's upsetting because when you see something as large as California, you'd like to be able to look at parts of California. But proportion is scale invariant. It's obvious, but then it could also be a little bit, you don't want to hear it. It doesn't matter on how big the thing is. The uncertainty associated with the estimated proportion does depend on the number of cells or samples that we obtain, and also depends on that unknown distribution. If it was perfectly structured and we got lucky, no uncertainty. We're generally going to assume that things are just dispersed. So now that we've digested that, hopefully, we're going to go a little bit deeper. And here we have a grid of 60 cells. We use 60 cells for our principal aquifers because that allows us to infer a proportion with relatively narrow error bars. Now imagine there's a target present at elevated concentrations, and it is present in exactly 1 cell's worth of the 60. So it's present in 1/60th, which is 1.67% of the area. If it's dispersed, keeping in mind in that first image, there's no uncertainty, right? You're going to get 1 blue ball and 59 white balls, no choice. The maximum uncertainty is associated with that dispersed grid. There's a 63% chance of detecting a target present in 1/60th of the aquifer. It's not 50-50, it's 63%. And part of the reason is you can get 1 dark blue, you can get 2 dark blues, you can get 3 dark blues. You're probably not very likely to get 4 or more dark blues. The only way to miss it is to get 0. There's a lot more possibilities of getting dark blue balls than just no dark blue balls. So it kind of adds up to 63%. Now we're going to change the question. And we're going to change the question because that helps us with interpreting the data that we collect. And the question we're going to ask is the following. What is the size of the target such that there's an equal likelihood of detecting it and an equal likelihood of missing it in a grid of 60 cells? And the answer is 1.15%. If a dispersed target is present in 1.15% of the area, then there's a 50% chance of detecting that target. Now, we have 25 grids. We have 25 principal aquifers. Well, that's 1,500 samples, and I want to remind you, it doesn't matter where the target is located. It doesn't matter how it's distributed. Imagine there's a target present in 1.15% of the area. You don't know in which one of those 25 grids. It could all be in one of those grids. It could be in all 25 of those grids, or it could be in every cell of all 25 grids. It doesn't matter its location nor its distribution. If a dispersed target is present in 1.15% of the area, then there's a 99 point and there's 5 nines there chance of detecting that target. The most likely number of detections is 17, which is 1.15%. It could be more, it could be less. The chances of 16 and 18 are nearly as high as 17. 15 and 19 are also up there. The chances of it being 10 or 34, not so much. In fact, the chances of it being 0 is 1 in a million. We're not really going to miss it. However, in any one of those grids, we're going to miss it half the time. That's really important. So if there were a target present in all 25 grids and it's 1.15% of the area, we have to, on average, miss it half the time. There's a 50-50 chance in any one grid. Well, 1.15 is pretty close to 1, so we're going to go for 1%. And 1 is obviously less than 1.15, so if a target is present in 1% of the area, then it's unlikely to be detected in a single 60-cell grid. It's less than 50-50. However, a target present in 1% of the area is unlikely to be missed in 25 60-cell grids, and now there's 4 nines after the decimal. At a national scale, we will define a 1% threshold as frequently detected. And the reason we want to do this is, as I'll show in a moment, we sample for over 500 constituents. We're not going to write research papers on 500 constituents. We'd like to give constituents permission to leave the report. So we're going to use frequently detected as a metric. That's equal area grids. Now let's turn to constituents and human health benchmarks that we use to place those concentrations into context. The NARCO program at the public supply wells, not every well we sample, but at the public supply wells, we sampled for 502 water quality constituents. Many of them have a human health benchmark, many do not. Those constituents have geologic or natural sources. They have anthropogenic or human sources. Many of those anthropogenic compounds are organic compounds requiring the use of low-level detection methods, typically at the 10 parts per trillion level. Many of those 502 constituents were considered that's our new analytes or constituents of emerging concern. They include pharmaceutical compounds, human hormones, and radiochemistry. Some radiochemicals are regulated, but there are many out there that are not. If you recall, the third question that I said we wouldn't spend a lot of time on is what are the hydrogeologic factors affecting groundwater quality? Well, we use geochemical indicators to help get at that. Those geochemical indicators include the major ions, redox, pH, dissolved oxygen, and temperature. One of the outstanding features of what we've been able to do is the evaluation of groundwater samples for multiple tracers of groundwater age. Every one of our samples was intended to be sampled for tritium, which is a marker of groundwater that was been introduced since the early 1950s, either SF6 or CFCs, depending upon the location in the country, carbon-14, which allows us to get water that's thousands of years old, and noble gases. The noble gases include helium, which allows you to get to hundreds of thousands of years, but helium has a lot of confounding factors. Those confounding factors are partially sorted out through the collection of other noble gases. We evaluate untreated groundwater. We don't evaluate water that's put into the pipes. We don't evaluate groundwater coming out of the taps. This is a source water investigation. What is the quality of groundwater used for public supply? Excuse me. We've collected a sample. We've sent it to the laboratory evaluates it. We get a concentration. We're going to compare that concentration to human health benchmarks. Why human health benchmarks? Because the taxpayers have paid for this. In addition to all that labor of collecting the samples, there's an equal dollar cost to analyzing it in the laboratory, and there's another equal dollar cost to tracking all this information and interpreting it. All told, these 25 principal aquifers represent about $25 million of taxpayer investment. So we're going to compare these constituents to water quality benchmarks that are relevant to human health. The first one we look at are maximum contaminant levels, or MCLs. These are regulatory standards. They're legally enforceable. They're established by the U.S. Environmental Protection Agency. They're applicable to delivered water. Source water, such as groundwater, can be mixed or treated prior to delivery. In addition, water quality can change along the piping system. And states can set more stringent standards. The next type of benchmark is non-regulatory. We can evaluate the water quality benchmark for a constituent by following a procedure established by the Environmental Protection Agency. And the underlying information, in part, is toxicological studies that provide concentrations that could be harmful to people. And those toxicological studies can either be judged to have higher or lower certainty with respect to human health. So if the certainty is relatively high, we'll call it tier 1. If the certainty is low, then the procedure calls for dividing by another factor of 10. So the concentration that you get for benchmark isn't necessarily indicative of causing harm. It reflects uncertainty or the precautionary principle. And so the concentrations associated with what we call tier 2 are typically an order of magnitude lower. So if there's lower certainty, we call it a tier 2. We're going to focus mostly on MCLs and tier 1s. I'll speak only briefly about tier 2s. So now what we're going to do is compare the environmental concentration with a benchmark. And we can judge that concentration to be either high, moderate, or low. If we have an ensemble of data, we can also look at the proportion that's high, moderate, or low. Very simply, a high concentration exceeds a benchmark, whether regulatory or non-regulatory. A low concentration is judged to be low if it's 1/10 of the benchmark for an organic and 1/2 of the benchmark for inorganic. Organic constituents are generally introduced by people. Nobody likes hearing that there's pesticides or gasoline or human hormones in their water supply. I can tell you that they're ubiquitously present, but not ubiquitously present at elevated concentrations. Inorganic constituents occur naturally. They can be introduced by people, but by and large, they're naturally occurring. So we have a higher standard to kind of cross to be judged as above low for those inorganics. A moderate concentration is neither high nor low. Now later I'll introduce to you why we're introducing elevated concentrations. If a concentration is either high or moderate, we'll call it elevated. And I'll cover why we're doing that. So we're going to focus on elevated concentrations, keeping in mind that an organic constituent can be judged to be elevated at that 1/10 of the benchmark, whereas an inorganic is 1/2. So we have equal area grids. Every well is in an equal area cell within a given principal aquifer. We have benchmarks, MCLs, tier 1, tier 2. We can judge a concentration to be high, moderate, or low. How will we take the measure of groundwater quality at either the principal aquifer scale or the national scale? The simplest metric is detection frequency. What are the proportion of wells with elevated concentrations? And typically that's how NAWQA has reported out its results, as have others. However, proportion does not account for differences in size, neither area nor population between two different principal aquifers. So let's use the state model just for a second rather than a PA. Now we're going to put together a national story. We're going to need to account for the fact that California is bigger in area. We need to account for the fact that California has more people than New Jersey. So when we correct for area, we're going to call it prevalence. We're going to define prevalence as the proportion of an aquifer from an areal extent with elevated concentrations. We're not going to worry about the fact that the aquifer thickness changes from place to place. At the scale of a principal aquifer, let's recall we're using equal area grids. Every well in an equal area grid for a single principal aquifer represents an equal area. Therefore, for a single PA, prevalence is equal to detection frequency. However, at a national scale, we must account for the differences in areal extent to get prevalence. So prevalence can be viewed as the area-weighted average of those PA detection frequencies or PA prevalences. The next metric is for population. There's a cascade through here, so I'll ask you to kind of let me walk you through the word slide. We're going to talk in terms of the population potentially affected. It's just a metric. It doesn't mean this number of people are seeing elevated concentrations. And the first thing we need to recognize is that the population dependent on groundwater in each PA varies. So even if it's not just a question that one principal aquifer has more people and another has lesser people, we also need to account for how much of that population is depending on groundwater itself. Well, in most water supply systems, there's a mix of surface water and groundwater. So it's not really broken out. So we do know how many people are in public supply, and we do know what proportion of the public supply is groundwater as compared to surface water. So we're just going to define the population dependent on groundwater as the total population of public supply times the proportion of that public supply that is groundwater. It's a simple computation. It's just a lot of words to get there. Now, at the scale of a PA, we're going to simply define that the population potentially affected is equal to the prevalence, the detection frequency, times that groundwater dependent population. So even though New Jersey is a small place, it still has a lot of people, right? And so we're going to sort of account for that. Similarly, the Edwards Aquifer is a really small footprint, but it accounts for a large amount of supply. At a national scale, we can then simply sum up that population potentially affected. So we've got three metrics: detection frequency, you often see it; prevalence, not as often; and population potentially affected. That's the study design. Right? Equal area grids. Given the fact that every well carries equal weight, we know what's going on in the principal aquifer. We can scale up by accounting for either area or population. Before we even get to the metrics, let's just do some simple bookkeeping. And I say simple bookkeeping. We've got 502 constituents at 1,500 wells. there's a lot of information flowing and making sure that all that information flows. We have 41 geogenic constituents that we analyzed for, of which 23 have either an MCL or a Tier 1 benchmark. We have 440 anthropogenic constituents, of which 153 have an MCL or Tier 1 benchmark. 41 plus 440 is 480. We sampled 502. That reflects those geochemical indicators and the markers of age. Now let's ask the question, of those geogenic constituents, of those anthropogenic constituents with an MCL or Tier 1 benchmark, how many were detected at an elevated concentration? How many were frequently detected, which is 1%? Of the 23 geogenic, 16 were detected at an elevated concentration and 10 were frequently detected. Of the 153 anthropogenic constituents, 12 were detected at an elevated concentration and only 1 was frequently detected, and that one is nitrate. So of those 440, most of those are organics. None of the organic compounds were detected at an elevated concentration in our 1,500 wells. It doesn't mean it's not out there, but it means that the area of the nation that has those elevated concentrations is so small that we don't sample it. Now let's turn to Tier 2 for just a moment. There are 7 geogenic constituents with a Tier 2 that would be a threshold of lower confidence. 6 were detected at an elevated concentration, and all 6 were frequently detected. 191 anthropogenic constituents have a Tier 2 benchmark. And we get to that 191 by looking at things like, well, if it's a hormone, how does that hormone concentration compare to what you find in the human body? Is it 1/10 that concentration? Or it's a pesticide degradant, and we look at the molar ratio of the parent and ask, what would have been the pesticide concentration of that parent, and how does that compare to that parent's threshold? So we're just kind of giving every opportunity to put every constituent that we can into context. Of the 191 Tier 2 anthropogenic constituents, 5 were detected at elevated concentrations, and exactly 0 were frequently detected. So now let's look at the 153 anthropogenic compounds with an MCL or Tier 1, the 191 with Tier 2. Only 1 of that 340 plus was, or actually 0 were frequently detected. Just nitrate was the anthropogenic. We've sampled exhaustively for organic compounds. Before Knockwood began all this work, this knowledge wasn't there. Tremendous resources were invested in how to even analyze for all of these constituents. We can say with confidence that these constituents are prevalent at any concentration, but they're not prevalent at elevated concentrations, recalling that to be crossing the threshold to elevated is 1/10 the benchmark. I can also tell you in most cases less than 1/100th the benchmark. Again, we're sampling untreated groundwater, not water delivered to a consumer. So that's before we even get to the metrics, we're starting to see a story emerge. Let's continue to look. Geogenic constituents have a detection frequency of 36%, a prevalence, which is area weighted of 41%. The anthropogenic constituents are coming in at 8 and 6. So you can see that geogenic constituents are detected more frequently and have a higher prevalence. If we sum up all the wells, 41% are high for or elevated for some constituent, 45 by prevalence. If you look, 36 plus 8 does not equal 41, because a single well can have both an anthropogenic and a geogenic constituent at an elevated concentration. This is one of those slides I'll ask you not to read the graph. I'll walk you through it, I promise. This is the population potentially affected by groundwater contaminants. It's not how many people are drinking groundwater with elevated concentrations. The y-axis goes up to 40 million people. The blue bar is any constituent. The brown and gold is geogenic. The light and dark green is anthropogenic. Let's look at the geogenic. Roughly 32 million people are potentially affected by geogenic contaminants. Notice that the gold and the brown bars are of roughly equal height. The gold are moderate concentrations. The brown is high concentrations. It's about 50-50. If you look at the anthropogenic bar, you'll see it's about 7 million. 7 million last time I looked is a lot lower than 32 million. But you'll see that the green bar, the light green bar, is a lot more than half of that height. And again, we'll kind of get into this. I'm just going to try to lead you through it. So just as we saw it in just the compound counts, we now see detection frequency, prevalence, population potentially affected. Geogenic constituents are more impactful on groundwater quality relative to human health than the anthropogenic constituents. Now we're going to drill down just to kind of see where we are. Right? We just compound count. We looked at prevalence, detection, frequency, population. Now we're going to look at all the constituents which are frequently detected. We're not going to look at 502. We're not going to look at even the 16 and the 9, whatever it was. There are 3 geogenic trace elements that have a maximum contaminant level, or MCL. Arsenic is coming in just about 15%, whether it's detection, frequency, or prevalence. Fluoride's coming in at just about 4. Uranium's coming in at just around 3.5. There are 3 geogenic trace elements that do not have an MCL, but they do have a tier 1 benchmark: manganese, strontium, and molybdenum. Manganese comes in at 9% roughly for detection frequency and 17% for prevalence. The reason is that the glacial aquifer, which covers the northern quarter of the United States, has a high prevalence of elevated concentrations of manganese. That high prevalence weights the nation. Strontium coming in around 6, molybdenum coming in around 2 to 3. We're not done with geogenic constituents yet. Radium-226 and radium-228 are 2 constituents, but they're regulated as a sum. They're coming in at 7 to 8%. Gross alpha activity is adjusted for the presence of uranium, because uranium has its own MCL, coming in at 5 to 6%. Gross beta is also adjusted. It's a more complex set of adjustments, coming in around 1%. We can finally get to the anthropogenic constituents, having gotten through this list of geogenic. Nitrate is the one constituent which was frequently detected at elevated concentrations, coming in at 6% detection frequency, just about 5 for prevalence. Recall that no single organic constituent was frequently detected at elevated concentrations. We're not giving them permission to leave the report. All organic compounds are those blue balls that we just saw. If the concentration of any of one of them is elevated, that well is marked as having an elevated concentration. Roughly 2 to 3% of the wells, either by detection frequency or prevalence, have elevated concentrations of some organic. So we're seeing the same recapitulation. As a group, geogenic constituents detected more frequently, more prevalent, potentially affecting more people. But then we look at an individual basis. Again, we see many of the geogenic trace elements are greater. But I want to stop and pause. Let's look at nitrate. We all read about nitrate fairly frequently in the newspaper. It is a significant groundwater quality issue. Let's take it as a benchmark. We're looking at that 4 to 6% range, and ask the question, how many of those constituents in the list above come in about equal or greater than nitrate? Well, arsenic, fluoride, uranium, manganese, strontium, you could say molybdenum, yes, maybe not. Radium-226 plus radium-228, adjusted gross alpha, all equal to or greater than nitrate. Let's look at organics. People don't like organics in their water. Fair enough. We've evaluated their elevated concentration at 1/10 the benchmark, coming in at the 2 to 3% range. Ask the question of the things on the list that we haven't already mentioned, which ones now join. And I'd say molybdenum, if it was on the cusp before, is now part of it. And you could argue that adjusted gross beta still doesn't quite make the list. There's a long list of geogenic constituents you might not have heard about, but they're equally as important with respect to human health benchmarks as nitrate and any organic compound. The next plot has a lot of information. Again, I'll ask you to please not read, otherwise I'll talk really fast. The y-axis is the population potentially affected. The first 3 bars are the geogenic trace elements with an MCL: arsenic, fluoride, uranium. The next 3 bars are geogenic trace elements with a tier 1 benchmark, non-regulatory: manganese, strontium, molybdenum. The next 3 bars are the geogenic constituents have a radioactivity and an MCL to place that concentration of that MCL into context: radium-226 plus 228, adjusted gross alpha, adjusted gross beta. The last 2 bars in green are anthropogenic constituents: nitrate and any organic. Next thing I'll ask you is just look at the height of the bars. The 3 bars that seem to stand out to me are arsenic, manganese, and radium-226 plus 228. Look at the nitrate bar coming in at just over 5 million people. How many constituents literally stand up as high? And then joining those 3, I think we could add strontium and adjusted gross alpha. Let's look at the organics. We care about it. I don't know about you, I don't want to see organics in my water. What constituents stand up as tall? And then suddenly I think we're adding fluoride, we're adding uranium, we're certainly adding molybdenum, adjusted gross beta, maybe still doesn't join. So population potentially affected, like prevalence, like detection frequency, tells us the same story. Now, before I move on, I want you to look at the last green bar, organics. Look at the height of the light green. Look at the height of the dark green. Because now this is a hypothesis. I haven't tested it. I'm not even sure how I would test it. People generally don't like organics in their water. If a well has a high concentration of an organic, then that well is either shut off or it's mixed with other wells or it's treated. A utility needs to report to the Environmental Protection Agency an exceedance of a benchmark of an MCL at compliance points in their distribution system. They don't have to report a high concentration at the source because they can dilute it down. They've treated it. If they let the USGS sample that well, that value is now out there. So it's either shut off or perhaps when we call up, they don't give us permission to sample a high well. It's a hypothesis. However, it's 1/10 the benchmark. No worries, they allow us to sample it. So the reason we have decided to use elevated concentrations rather than high concentrations is that potential bias in that kind of high versus elevated, or high versus moderate. So what we're trying to do here is answer the question, which constituents are most prevalent at elevated concentrations? To get at this question, what is the quality of groundwater used for public supply? Every constituent is being evaluated from an equal footing. We're trying to get past some of the biases that might have been introduced. Reminder, untreated groundwater, not delivered water. That's the national scale results. Now let's look at the principal aquifer scale results. These are selected results. There's a lot more in the paper that I mentioned. And in that paper, it references 16 papers that we've published on either individual constituents or large regions of the country. Now I will slowly walk you through this, and I'll introduce each one of those legend entries. The first ones we'll introduce are the Western unconsolidated. Let me see if I can. No, it won't work here. These are the Western unconsolidated aquifers. We've got the California coastal basins, the Central Valley, the Basin and Range, the Rio Grande, and the High Plains. What they all share is in a relatively arid climate. They're relatively open systems with the exception of the California coastal basins. They're generally oxic, and at depth they're generally alkaline. From a national perspective, they're of moderate thickness. Other aquifers are a lot thicker, a lot deeper. The next set I want to introduce for you are the Stream Valley West, the Glacial, the Stream Valley East. The Stream Valley West are those brown lines around the light yellow color crossing the high plains, and you can see that the symbol color is a brown rather than a blue. The Eastern Stream Valley is mostly the Ohio River Valley, sitting just below the glacial deposits. The glacial deposits are crosshatches, and they're squares rather than circles. When we began this, I would have thought that the Stream Valley West was going to look like the High Plains. It does not. And one of the reasons it doesn't is because they're really thin and they're in proximity to water. And the water quality, as I'll show, for the Stream Valley West and for the Stream Valley East look a lot more like the glacial deposits than they do like anything else. The next group I'll share with you in darker green, these are the interior sandstones and carbonates. This is the Colorado Plateau and Wyoming basins. I'm not sure why the USGS on its principal aquifer map lumped the Wyoming basins in with the Colorado Plateau, but they have. Then we have the Trinity and the Edwards Trinity aquifers, which are sandstone and sandstone carbonates. The principal aquifer defined by the USGS lumps the Edwards in as well, but Maryland Musgrove here in the USGS Water Science Center in Austin separated them out to reflect the Texas perspective on these. So numbers 12 and 10 and 12 are sandstone and sandstone carbonates. This is the Cambrian Ordovician. The next set in blue are carbonate aquifer systems. Actually, before I get to the carbonates, these rocks are just generally a whole lot older than any of the other rocks. They're Cretaceous and older. In fact, this is the Cambrian Ordovician, as its name implies, is Cambrian Ordovician in age. Next, we'll look at carbonates. you can see in here, there's some blues distributed amongst the browns. In the mountains of the basin and range are carbonate rocks. There often are springs, or there used to be springs where they've now put wells, and they do serve as public supply. The Edwards, the Ozarks, the Floridan, the valley and ridge along the Appalachian Trend. The Biscayne, a tiny footprint, number 23, but it's a very important source providing a large number of people. The crosshatch here are is called the Superficial Aquifer, but these yellow dots reflect the fact that it's barely used and it's only used along the coast. It's essentially a marl just sitting on top of the whole system. So it's relatively thin and can only really be used with deeper pockets. The olive colors are the principal aquifers that lie along the Atlantic and Gulf coasts. The North Atlantic coastal plain, the Southeast coastal plain that extends up through here, the coastal lowlands. We merged the Mississippi embayment and Texas coastal uplands. That's this lighter green. The only difference between the Texas coastal uplands and the Mississippi embayment rocks is the boundary of Texas. But otherwise, they're depositionally the same. And then finally, in the purple color are the Columbia Plateau basalts in the northwest and the Piedmont Blue Ridge crystalline, which you see in the Appalachians. The Piedmont Blue Ridge crystalline doesn't rise to one of the top 25 principal aquifers for public supply, but it's number one for domestic wells. And when I was designing this, I was asked by those managers that I report to, just put it in. So we also put that one in, which is probably why we get to 85 and up to not up to 90% in essence. I'm going to again ask you not to read this because I will walk you through it. Again, recall that we have these groups of principal aquifers. We're not going to look at the individual principal aquifers. Western unconsolidated, stream valley and glacial, interior sandstone and carbonate. Let's start with those. The y-axis is the prevalence at either high or moderate concentrations. And when we look at all of the height of these bars in these three groupings, representing, I think, 12 or 13 PAs, the height of those bars is 40 to 75%. Then we go to the other three, the carbonates. The carbonates are distributed across a really wide range of climatic conditions. Gulf and Atlantic coastal clastics, largely Cretaceous and younger, hard rock. We can see the height of the bars is relatively low, 15 to 35%. So we can do a little bit better than depends already. If we're dealing with Western stream valley and interior sandstone carbonates, we have relatively high prevalence. If we're dealing with coastal and hard rock and carbonate, we're dealing with relatively low prevalence. And we can say this because we have systematic sampling on an equal area grid. So that's just a kind of a quick picture of the principal aquifers, how they compare to one another. Now let's look at constituents also at a national scale. Arsenic was present both in detection frequency and by prevalence, about 15%. But the prevalence exceeds 40% in 4 western unconsolidated PAs. Those 4 are the Central Valley, the Basin and Range, the Rio Grande, and the High Plains. What those 4 have in common is that the climate is arid, they're oxic, and at depth they're alkaline. Arsenic has 2 mechanisms by which it's mobile in groundwater. One of those mechanisms is desorption from sediment under oxic alkaline conditions. So at the beginning, I said I'd say a little bit about the factors affecting the groundwater quality, and here we're just sort of highlighting some of the outcomes. Manganese was prevalent 17% nationally, a much lower detection frequency. The prevalence exceeds 30% in the glacial, Stream Valley West, and Stream Valley East. When we say that manganese has elevated concentrations, we're also simply saying that the conditions are reduced. Groundwater conditions can become reduced because there's a lot of standing water, there's a lot of organic matter, and the oxygen is consumed before it ever gets into the groundwater system. Or the oxygen can be consumed because it's traveled along a flow path and has been consumed along its migration through the subsurface. What the glacial, Stream Valley West, and Stream Valley East all have in common is that the wells are typically very shallow. They're just a matter of tens of meters. Some of these wells are hundreds of meters. And they're almost all proximal to surface water. Almost by definition, the Stream Valley ones are proximal. And when you look at maps of the glacial system, in the eastern 2/3 of it, there's almost always standing water nearby. We'll finally finish with one more constituent, that's uranium. It's relatively low nationally, 3%, but its prevalence is 23% in the high plains. Elevated concentrations of uranium with this kind of prevalence are typically associated with sediment derived from granites. The High Plains Aquifer System is an erosional remnant of a plain that once extended back to the Rockies. These are sediments simply derived from the laramide uplift. So we're going to switch now from three interesting constituents. We looked at sort of the principal aquifers at a broad scale. Now let's just focus on a few principal aquifers that really seem interesting. The Cambrian Ordovician has a prevalence of radium at elevated concentrations of 66%. Now there's some margin of error here, right? We have 60 wells, so it can be plus or minus. Elevated concentrations can occur in anoxic, highly mineralized groundwater. That's an association because it takes time for radium to accumulate at elevated concentrations. 60% of the groundwater in the Cambrian Ordovician, again, that's the circled area with the ears, 60% of the groundwater is anoxic. We can say that because we have an equal area grid. Every well represents an equal area. We can talk about 66% prevalence for radium at elevated concentrations. We can talk about 60% being anoxic. Well, 60 is pretty darn close to 66. 65% of the groundwater is Pleistocene in age, more than 12,000 years. We know that because we sampled from multiple traces of groundwater age, and then we fit lump parameter models which help derive age distributions. So we have an age distribution for every one of our wells. We can assemble up that information. 65% is Pleistocene in age. And in fact, more than 25% of the groundwater in the Cambrian Ordovician is greater than 100,000 years old. This is fossil groundwater, in essence. We're not done with the Cambrian Ordovician. The prevalence of elevated gross alpha is 49%. Radium-226 and radium-228 are both alpha emitters. So that's our explanation for that. So now we're done with the Cambrian Ordovician. We're going to focus now on California coastal basins and the Valley and Ridge Piedmont carbonates. So again, I'll remind you, these open circles labeled number 1 are the California coastal basins. And then these blue streaks, number 19, are those carbonates along the Appalachians. We sampled 25 principal aquifers. In 23, a geogenic constituent was the most prevalent. In only 2 was an anthropogenic constituent the most prevalent, and that anthropogenic constituent was nitrate. In the California coastal basins, 23% on an aerial basis has elevated concentrations. The history of California is one of people migrating from the east to the west, settling on the flats, planting crops, and over time, the most valuable crop is a suburban housing development. So invariably, except for a few places now in California, the California coastal basins are populated with people. The 23% that we see is a legacy of that agricultural period. The agricultural period included not only application of fertilizers, but also septic systems distributed across the landscape. The Valley and Ridge Piedmont carbonates, those blue streaks, is still active today as an agricultural province. It's karstic, just like the Edwards is karstic. Things move really rapidly. The nitrate concentrations that we're seeing there largely reflect the current land use. 14% of the resource has elevated concentrations. Let's summarize. Geogenic constituents have a larger effect than anthropogenic constituents, whether our metric is detection frequency, prevalence, or population potentially affected. If my information density, or I spoke too quickly, if the one take-home message, if there's none other, 3 unregulated geogenic constituents are prevalent at elevated concentrations. Those 3 unregulated constituents are manganese, strontium, and molybdenum. Together, those 3 potentially affect 18 million people, which is 20% of the population dependent on groundwater in the 25 principal aquifers that we evaluated. We evaluated principal aquifers that provide 85% of the nation's groundwater supply used for drinking. Additional attention may be warranted for these 3 constituents. The US Geological Survey is not a public health agency. It's not an epidemiological agency. It's not for the US Geological Survey to pursue it further. Right? The public health implications are sort of the next step in the chain. We've identified which constituents are prevalent, how many people may be potentially affected. And finally, elevated concentrations are more prevalent in some PAs than others. We broadly sampled these PAs. These are not targeted studies that could be questioned about how you put it together. Having done these broadly distributed PA studies, we can state that elevated concentrations are more prevalent in the west and central interior, 40 to 75%, less prevalent along the Atlantic and Gulf coasts, carbonates, and hard rock. I hope we've done better than it depends. With that, I'd be happy to take questions. And if I haven't answered your questions, there is a paper covering this material. Thank you.
Questions?